Hello everyone, my name is Maxim. I am presenting from Bellevue, Washington. I'm originally from Russia, where I studied physics, and later I received my computer science degree from Rio de Janeiro, Brazil. Today I'm going to talk about Temporal. I want to give you some history to kind of give you idea that it's not the project which we came up with overnight. It took probably like at least 15 years to get where we are. So I was tech lead of the Amazon messaging platform when Amazon was transitioning to microservices. And I was later that engine used for the Amazon messaging platform was used by the Simple Queue service when AWS appeared. I also was tech lead for the Simple Workflow service, which is which pioneered a lot of ideas that we are right now developing as part of Temporal. My co-founder of the Temporal, Samar, worked with me on a simple workflow, but later he came to Microsoft and he was tech lead of the service bus, Azure Service Bus. But as a side project, he wanted to bring to the people the same ideas of the simple workflow. So he developed Durable Task Framework, which later became so popular that Azure Functions team adopted that, and now you can use it as Azure Durable Functions. Later, we both joined Uber, and there we built two open source projects. One was Sharding, which was a messaging system, and later Cadence, which was re-implementation of the simple workflow ideas using completely different software stack and as an open source project. When Cadence became very popular, not only inside of Uber, where over 100 use cases were running on that within 3 years, but also outside, we quit Uber and started our own company called Temporal and forked the Cadence project as Temporal as an open source project. I was told that if you kind of presenting some technology, you have to give some social proof, and here's kind of some of it. So these are early adopters of our technology, and there are many more companies using that in production, but these are companies which went public about their usage. I gave presentation at multiple presentations. If you Google my name, you will see a lot of videos about which present Cadence and later Temporal and their programming model. But today I want to talk about the backend, about how cluster is organized and why we have all these multiple roles of the cluster in our architecture. And I don't expect you to understand that picture right now, but I'm pretty sure by the end of the presentation you will be able to make more sense out of it. But let's start from the beginning. What is workflow? And people have different definitions. There are like even standards and so on. My definition is that workflow is just a resilient program. And resilient, what it means that this program will continue execution independently of like in presence of failures. And you can have new deployments, you can have just infrastructure outages, data like availability zones going down, and you want your program continue execution. Usually, these programs are organized as like a sequence of tasks, and then it also has to react to external events and deal with time, because time is an important component of every business level process, and timeouts. I'm not going to spend time, as I said, a lot on the programming model, as I presented that multiple times. But if you never thought about Temporal or Cadence, here's the kind of basic idea. Basic idea that you just write code. Here's Java sample. We also support Go and PHP SDK, and working on other SDKs in the future. At least TypeScript and Python will be probably developed this year. This looks like normal Java code. Why is it a workflow? It is a workflow because full state of this program is fully preserved all the time. It's fully durable. So it means that if your program restarts or even backend service goes down and then back, your program will be in exactly the same state with all local variables, threads, and stack traces in exactly the same state. That's why you can go and write code we just call sleep, block and sleep for 30 days, and then unblock and do something after that. And if you don't need to care about process restarts and deal with databases and recovery of the state, because it's all done automatically by the Temporal. And again, as I said, I'm not going to spend more time on this. If you're interested, watch my past presentation or just visit temporal.io and go through our tutorials. So on a high level, any workflow engine, and again, it's not necessarily one which uses workflow as code, but also engines which use YAML, JSON, or XML, if you like those languages, they are kind of state machines. So practically, workflow is a state machine which defines in which order to run tasks and also react to external event if necessary. And if you represent the state machine, kind of what workflow definition does as a sequence diagram, we can practically say it asks tasks to execute in certain order. But if you want to implement the workflow engine, we need to have, this was like a more logical representation, but a physical representation will be some sort of code, some engine which will drive those workflows. So the way it's usually done is that you will go to workflow definition, the state machine, give it a state of the world and say, what are the next tasks, commands to run? And the command can be run task one, so it will go and run command task one. Then it will notify workflow definition that task one is completed. It will execute the state machine logic according to its definition and say, okay, now you need to run task two. In practical systems, you don't want to call tasks directly because these workers can be somewhere else. They might be not available, which run those tasks and processes. They can be issues with flow control because just they can be unavailable for some time. So or they can be slow. So you want to feed tasks in appropriate order. So using queues to dispatch tasks to the implementation is a very common technique. So you practically almost every practical workflow engine uses queues to dispatch tasks to workers, like worker processes which host those tasks. In Temporal, at least, we also run workflow code outside of the core engine. So we also use tasks and queues to deliver the request to workflow definition and then get commands back what to be executed. So practically all communication to workflow definition and task implementation is done through queuing. As I mentioned, the time is important because every task invocation should have a timeout. Workflow itself can have a timeout, and then we need to be able to execute operations like sleep 30 days. So we need some external timer service or timer queue, which will durably store those timers and then dispatch those timers. So workflow engine needs to have not only task queues, but also timer queues or timer engine and add tasks there every time some state transition happens. And then we also need to store state of the workflow itself. So every time we start a workflow, every update, practically we need to at least to create state in the state database. Then we need to create a timer, and then we need to put task for the task queue for the workflow definition to pick up. And when workflow definition gives a list of commands, we again need to update and create tasks and update the state. What's important to understand, and I think this is like a very important part of this presentation, is unless these updates across these multiple data sources are transactional, this engine is not very practical. You don't want to run on top of the engine which doesn't have transactions across all these components, because you will run in all sorts of race conditions. It's almost impossible to get rid of race conditions, because if you update state and then try to put task in a task queue, if update goes through and then update to task queue fails, so you will end up in a state which thinks there is a task outstanding, but task is not. If you put task in a task queue first and then you update the state, if update is slow, task can be delivered and processed by the time update went is going through, so it will be inconsistent and it needs to deal with all these edge cases. If updates to all these components are transactional, then all these race conditions just disappear. Your system becomes much simpler, and the application level code doesn't see all these edge cases, and it's actually simplified the programming model. But it's not only applies to the state machine, to the workflow engine implementations. Reality is that these days, majority of the engineers don't use workflow like orchestrator or like workflow engines to write their services. What they do, they use queues, they use databases, they use other data sources. They create these hodgepodge architectures of like different components, and there are no transactions across them usually. And the point is that like what I said about not having transaction, all this race condition applies to majority of the system, ad hoc system built by developers. And I think this is very important to understand that this is, if you're building system from these components, you're guaranteed to have edge cases and race conditions. So that's why having like a robust engine like Temporal underlying your architecture will simplify your life tremendously. So if you want to remember one slide from the presentation, remember this one, that workflow engines are hard, not because, mostly because they need to deal with multiple things like queuing, timers, and state, and updates across them should be transactional. So when you implement a workflow engine, because of all these transactionality requirements, majority of the existing implementations just use one database and even one process. And then, yes, if you have one database and one process, transactional requirements are easily solvable, and you can provide pretty robust engine. Obviously, this engine wouldn't be scalable because it will be limited to a single process or a single database. So if you want a scalable solution, first we need to decide what are the dimensions of scalability. Obviously, one dimension would be creating these huge workflows and have a single workflow which spawns multiple machines. For example, MapReduce is a technology which allows to write single kind of MapReduce pipeline, and this pipeline will be executed by thousands of machines. And you can think of this pipeline being more as a single workflow. For the use cases which we are targeting, we actually decided to go with approach when we're not going to scale up a single workflow instance. You cannot have single workflow which runs million tasks. Every workflow should be limited in size, but then we can infinitely scale out the number of workflows. So you can, if you need to run million tasks, you probably will have single workflow instance which will create 1,000 children. Each of the children can run 1,000 tasks. So you get your million tasks, but each of the instances will be bounded. So as soon as you say that each workflow instance is of limited size, you can go and start distributing them across multiple machines. So scaling out fleet of machines becomes practical because each instance is guaranteed to fit within a single machine. Obviously, if you want to have very large system, you need to scale out the database as well. So having single database instance will be a bottleneck. So if you have partitioned database and you have partitioned hosts which kind of maintain the state and perform all the operations and workflows, you can get to very scalable solution. But as I said, we need to maintain transactionality, and as soon as you start breaking your persistence into multiple databases, you wouldn't be able to, unless you start doing complex things like two-phase commits and so on across multiple databases, you wouldn't be able to provide transactional guarantees. So the kind of simple way to solve that would be to have one database per host, right? So if you have 4 hosts, we can distribute these workflows across those hosts. And every host will have its own database, which contain like its own queues, its own timers, and so on, and workflow state. And this way, we can guarantee transactions within each host and within each database. And that would be a pretty straightforward system to implement. That system wouldn't be very practical because it would be very hard to add and remove hosts. And I'm not going to spend much time on that. The standard way to solve this is just using sharding. So instead of physical hosts, we use partitions within the database, and we kind of over-allocate number of partitions. Then we kind of move those. Then we allocate those partitions to specific physical hosts, and we can move them around if necessary. And the same applies to shards within our hosts. So you can hash workflows to specific shard ID, and then use consistent hashing to allocate shard to a specific host. But to implement that, you need to know membership of your cluster, because if you need to allocate shards to hosts, you need to know which hosts are available in your cluster. So as soon as you do that, you need some mechanism for membership, and then you need routing layer, because if request comes in, and usually you don't want to have fat client-side library which understands topology of your cluster, so you need to have front ends which will know the membership of the cluster and route request to specific, for example, workflow ID 1 or workflow ID 2, it will know in which shard it's allocated and it belongs to, and then where this shard runs right now at which host. The sharding by workflow ID works. Problem is that it doesn't work very well for tasks for task queues. For example, if we have activities which listen on the task queue named foo, how do you get activity tasks waiting to be executed? If we store those activity tasks in every shard, you probably will need to go to all shards and ask them, do you have anything for full on task queue full? As we want to allocate a large number of shards because we want to support very large scale and we will over-allocate them, these type of queries become impractical. Even if you have them, like you cannot even aggregate them over a host because each shard practically requires a separate database query. Imagine you have 10,000 shards, so every time you do poll, you will need to go in like fan out for 10,000 database requests. So practical solution is to move queuing into the separate component with its own persistence. And that solves the problem of routing because you know where to which host to route and which host right now owns that queue, and you can have its own database with its own persistence for that. But it obviously introduces other problem, as I mentioned earlier, is that we lose transactionality. As soon as queues live outside of core shards of workflow state, we don't have transactions across them anymore, and we will have the race conditions which I described earlier. Obviously, one way to solve that would be to use some sort of two-phase commit variant, Paxos or Raft and so on, but it would introduce pretty significant complexity to the system, and also require like every component of that interaction to implement pretty complex protocols. The way we solved it in Temporal is that we don't use any of those transactions. We just rely on database. How do we do that? We use so-called transfer queues. The idea is that every shard which stores workflow state also stores a queue. So we will have, if we have 10,000 shards, we'll have 10,000 queues. And every time we make update to the shard, we also can update that queue transaction because it lives in the same partition. So if we need to start workflow, we will create a state for the workflow, and we need to create workflow task for the worker to pick up. We will add the task to the local queue to that shard. And then this will be committed to the database atomically, and then we will have a thread which will pull from that queue and then practically transfer that message to this queuing subsystem. And this way, we have transactional commit, and then we can later transfer that to the queuing subsystem. Obviously, this transfer can fail, we will retry, so it can create duplicates, but we have separate part of the system which will do the duping there. So that is kind of a very simple mechanism, but it allows us to have transactionality at the same time, don't rely on complex two-phase commit protocols. Other requirement that any reasonable workflow system should implement is ability to list workflows, right? Because you want to go and say, give me all workflows started by this user in the last 24 hours, all workflows which failed, and so on. Going again to all shards and 10,000 shards and asking them for, even if they have index, each of them has its index, for that information would be impractical. So the way to solve that is to have a separate indexing component. We use Elasticsearch. There is no, any indexing technology could be used instead. There is nothing special about Elastic that, but it's something which we just decided to use because it was open source. And we use the same transfer queue approach to transfer to commit so-called visibility records into the each shard, and then use transfer queue to transfer them to the Elastic. This mechanism has inherent delay, so Elastic index is always a few seconds, maybe like at least some time behind the actual update. So it's not, it's kind of converges to the correct with delay, but it's not atomically updated with when we commit message to the core shard partition. But there is a guarantee that if commit happened, that Elastic will be updated, and if it cannot happen that you will update the state and Elastic wouldn't be updated because of the transfer queue mechanism. As soon as you can list workflows, your users will ask you to perform batch operations. For example, I want to terminate all workflows which match this criteria started by this user. And you can program that from outside, just to make a list, get the IDs, save them to the file, and then execute some script to terminate them. But to execute that reliably, this is actually sounds like a workflow. And this is exactly what Temporal is doing. It implements this logic using a workflow. But this workflow is built into the core cluster, so it's kind of system workflow and it's implemented as normal workflow. It could be implemented outside, but we decided to implement inside because we want this kind of functionality to be provided as part of the core cluster functionality. So we have this worker role which performs system workflows like database scans and other like operations which can take long time reliably using standard temporal workflow abstractions. I showed this slide at the beginning of the presentation, and I didn't expect it to make sense out of that. But now I think you can understand why we have all these roles. So we have so-called history component, which is responsible for state transitions of individual workflows, has transfer queues to be able to transactionally create tasks. And then we have matching component, which is responsible for delivering tasks to like for queuing and matching pull requests coming from external workers to add task requests. And then we have front end because we need routing. We have Elastic because we have indexing, and we have worker component to implement background jobs. And then we have workflows and activities which are implemented by application developers using temporal SDKs. This architecture is pretty scalable and reliable because every single host in this architecture can fail, and it still will continue functioning. You can, because shards and history and service and matching will be redistributed automatically. We use cluster database like Cassandra, which can sustain node failures. Elastic is fault tolerant, but and front ends are stateless, so you can add and remove them anytime as well. But this system still has single points of failure in terms of like blast radius, because from a single bad schema deployment to the database can bring it down, update of the front end with a bug, and so on. So if you want to provide very high availability, we have multi-cluster deployment. In this case, we have asynchronous replication on the application level. And even the total meltdown of the cluster, or even like for example, Amazon region, unavailability of the region will not stop your workflows because you would be able to fail over your execution to another cluster and continue execution. This is for the next talk. I have it's pretty complex part of the system. The whole multi-cluster cluster setup. I can make multiple conference talk about that as well. Just to recap, Temporal is a technology, besides this awesome programming model of writing distributed code, like reliable code through using a programming language. It's highly scalable, and it scales the number of workflow execution, and it's consistent, which is very important to avoid all sorts of race conditions. And it allows to run pluggable activities and even workflow implementations outside of the cluster, which allows very, very high like flexibility, right? You can practically write your workflows and activities in any language. In the future, I'm pretty sure practically any language. This concludes my presentation. I want to mention that we are actively hiring, and you can reach our project on over Temporal.io or directly on GitHub. We also have community forums for support, and you can reach me or our company on Twitter. Thank you.